Hello, do you see now the screen?
Yes.
Okay, so today we will start a new chapter. This chapter will offer numerical techniques based on iterations to solve for a linear system and a nonlinear system. So if you remember in chapters 9, 10, and 11, we developed techniques to find the exact solution of a linear system. Okay, but now we will develop techniques based on iterations. So first, the objectives of this chapter is to use iterative methods to solve for a system of linear or nonlinear equations, and we will see when these methods are attractive. So already we have introduced several engineering problems requiring the solution of a linear system. So if you recall the system of masses with springs and we want to solve for displacement, the concentration problems, and the electric problems. So all of these problems require the solution of a linear system. Now, what we will do is that we will develop new techniques based on iterations to solve for linear systems. The first method is the Gauss-Seidel method, in which we solve for each variable by iterative procedure. How do we do this? If you look at this system, it's a linear system, and we want to solve for x1, x2, x3. So you can say, for example, if I start with an initial guess for x1, x2, x3, I can find the updated values for x1, x2, x3 by iterations. So first, if I want to get an updated value for x1, from this equation, I can write that a11 x1 plus a12 x2
plus a13 x3
plus a13 x3 equals to b1. So now if I want to get the value of x1 from this equation, I will just have to take these terms to the other side, okay, and divide by a11. Then I obtain an updated value for x1 using values for x2 and x3 from the previous iteration, okay? And once I update x1, I have two choices. If I am working in Gauss-Seidel method, then I should replace x1 by the updated value. So now when I want to compute x2, I will use now the second equation to compute x2. Okay. I want to tell you that you don't have always to use the first equation to get x1, the second to get x2, the third to get x3. You can, for example, use the first equation to get x2, for example, and then you will update the x2 first, then you find x1 updated, then you find x3 updated. But the idea is that in general, we follow the order, yani. But it's we are not obliged to do this, okay? So we will see together after that sometimes we can switch, we can do pivoting of the equations in a way to ensure convergence. So in this case, the first equation, for example, will be used to find another variable than x1, etc. Okay. So here, the rule in general, we follow the order, but as I told you, we can switch, and it will not. I will always get a solution, but it will be different because the choice of the equation will induce. If we vary the equations, this will give us numerical variation because of round-off errors. Okay. If we don't have round-off errors, we expect to have the same solution if we start, if we use this equation for x1, or we use it for x2, or we use it for x3. But because of numerical errors, we might have problems. This is why a good arrangement, a good choice of which equation to use can, with which variable, can affect the result. And we will see a technique that can guarantee convergence of the method in the following slides. So now, for Gauss-Seidel method, the idea is that once I update a variable, let's say I got x1 from use of equation 1, I use now the updated value for x1 into the computation of x2 at the current iteration. While for x3, it's not yet updated, so I will use the old value. And now once x2 is updated also, so when I want to compute x3, I will use the updated value of x1 and the updated value of x2. So this is the Gauss-Seidel method. And in this case, to assess if I reached convergence or not, at each iteration, I should verify that the approximate error is verified, is lower than the criterion, stopping criterion, for the 3 variables. It's not enough to have epsilon approximate smaller than epsilon s for 1 or 2. I should have it for the 3 variables. So if I'm checking convergence, if just for x1 I didn't reach the criterion, I can directly stop and say I should iterate again. No need then to find what is epsilon for the 2 others, unless I want to track the variation of the error. Okay. So now let us consider.
Doctor,
Yes.
you mean we try to calculate the error 3 times for each
Yes.
X?
Exactly. You should compare x1 new with x1 old, x2 new with x2 old, and x3 new with x3 old. I mean by all the previous iteration, just the previous one. For example, here at iteration j and j minus 1. Okay, so this is the general rule for epsilon, but you should repeat it for the 3 variables. I will vary from 1 to n. So if you have here n is 3, you should compute 3 approximate errors, 1 for x1, 1 for x2, 1 for x2. Okay. So let us consider an example. Using Gauss-Seidel method, we want to solve for x. So this is the A matrix. And we have A times x equals to B. This is B. And we want to solve now. So this is a linear system. We have several methods now to solve for it. We can solve using Gauss elimination. We can use solving LU factorization. We can solve using the inverse matrix. If you remember that, we can say that x equal A minus 1 times B. And now we introduced a new method, which is all other methods are not iterative. They are numerical techniques that we developed. But now we will use iterative solutions. So this is why we should, at each iteration, check for the criterion of convergence. So if we start by initial guess of 0, 0, 0, then we can calculate, we can start to find the values of x1, x2, x3 at the first iteration. So to start with x1, we will use the first equation. Okay, so first equation will give us that 3x1 minus 0.1x2 minus 0.2x3 equals to 7.85. So if we rearrange terms, we get that x1 at iteration 1 is b1 minus 0.1 times x2 minus 0.2 times x3 at the previous iteration. So here, for the initial guess, we have x2 0 and x3 0. So we can compute that for the initial, for the first iteration, x1 is 7.85 over 3. Now, once x1 is, since we are using Gauss-Seidel method, once x1 is updated, now to calculate x2, we do b2 minus 0.1 times the updated x1, which is which we got from this iteration here before, and then we do minus 0.3 times x3. We use x3 old. So now in the first iteration, we will use here 0, the initial guess. And then we get the updated value of x2. Now both updated values will be replaced into x3 to get the value of x3 at the first iteration. So let us see it here in the coming slide. So first we compute x1. We use x1 updated into the computation of x2. And then we got x2 updated. And then to find x3, we replace by x1 updated and x2 updated to get x3. We are done with the first iteration. In general, the approximate error, we can calculate it, but it will give a good result starting. We expect to have good results starting from first iteration, because in general, the initial guess by chance was very close. But it's hard it's not easy to have a good initial guess for the three variables. And in general here, for this assumption 0, 0, 0, for this initial guess, the approximate error is 100%. So it's very large. And now we can start to decrease it as we proceed. This method is not guaranteed to converge always. Sometimes it can diverge. How we know? We can calculate new errors if we see the pattern of error. If it's increasing, so we might have divergence, or we might the solution might take time to converge. This is why we will develop a technique that will guarantee convergence, and we'll see how.
Doctor, here if you told us do one يعني مثل test one, do one iteration, the first error, we compare the second and the third iteration.
Look, since this was confusing for you, I'll specify from now on. I'll specify the iteration. Now I will tell you, let's say, do 2 iterations or do 3 iterations, because this was a little bit confusing. But in general, it's just like a convention. مش إنه it's always like this. It depends on the convention you use. يعني في عالم تعتبر إنه it's an initial guess. I will not consider it. في عالم بتقول إنه okay, low initial guess, I can consider it an estimate and then do the comparison. So it's not something standard. It depends on the convention you take. To not be confused, I will tell you, let's say, do 2 iterations or do 3 iterations.
Okay, 2 iteration, but do we start with
لا يعني اكيد الجاس ما بعتبره iteration اكيد. يعني الجاس ما بعمل شيء. First iteration يعني I got x1, x2, x3 for the first time. Second iteration I am getting new values for x1, x2, x3. اكيد وقت احكي عن number of iterations ما بحسب الجاس. يعني هو مثل iteration 0 الجاس. I don't count it. Okay. So here now I want into second iteration, I want to update values of x1, x2, x3. So to start with, I use as the values I got from the previous iteration of x2 and x3 to update x1. So from the previous iteration, I got that x2 is minus 2.7945 and x3 is 7.0056. All I have to do is to replace them here. I update x1. And once x1 is updated, I will use the updated value of x1 to compute x2 at iteration 2. While since x3 is not updated yet, I use the old value. And finally, for x3, now since I updated both x1 and x2, I will use the updated values into the computation of x3. And again, once I get the 3 updated values, now I can calculate the approximate errors for each variable. Now, as I told you, in case just you should make sure if you reach stopping criterion or not. Once you can stop here. And already the first variable was not converging, so I can stop here and say I should iterate more. Okay. Now, if I do a third iteration, I will repeat the same procedure. Now I will use the values of x1, x2, x3 of just iteration 2. So I will replace x2 by minus 2.4996, x3 by 7.003, and then I will update x1. Once x1 is updated, I should use it in the second iteration. Just let me check here. Okay, here. They did yes. So here this is 3 point. So it should be 3 here. Okay, or if هون يمكن عملوها approximation ل 3 بس هي 2.9906. Okay. So we replace the updated value of x1 here, and since x3 was not yet updated, then we replace it by the old value. We get x2. And finally, same procedure to get x3, I replace by the updated value of x1 and the updated value of x2. Here they just did the round, okay? They round the solution to the closest digit, but it is, to be accurate, it's 2.4996, okay? And then now I check, once I'm done with the third iteration, I check for the approximate error. I compare the solution I get in the third iteration with values obtained in the second iteration, and it worked well. I am, for the 3 variables, I reached my criterion and I reached much lower values, so it's very good. Okay. In general, Gauss Seidel it converges in a fast way because I am using updated values. So using updated values of x1 and x2 into computation. Yani first in x2 I used updated x1, and in x3 I used updated x1, x2 will help into a faster convergence. But what is the condition? The condition is that the system is already converging, and it's not prone to divergence. In case I have a system that where the errors start to oscillate and it might diverge, it's not recommended to use Gauss Seidel. Okay, because Gauss Seidel will take advantage of a converging system to make it faster in convergence. While if I have an oscillation behavior, then it's suggested to you to not use updated values, or also, as you will see after, we might do also under relaxation. Okay, so now we will introduce another method that is very similar to this one, but instead of using the updated values into the computation in the same iteration, okay, we will not do this. And we will, in each iteration, we will use for all variables to calculate, to compute x1 new, x2 new, and x3 new, we will use the old values. Okay, this is called the Jacobi method. So now, the only difference between the Gauss Seidel and the Jacobi method is that I do not use updated values of x1 and x2 in the current iteration. I just use always the old values. And here, this is the comparison. This is Gauss. This is Gauss Seidel. This is Jacobi. Okay. The equations are the same. And here, I use the first equation to compute x1, the second to compute x2, the third to compute x3. So exactly same equations. The only difference is that when I substitute here, of course, in computing x1 for both cases, I will substitute the old values because they are not updated yet. Now, if I'm working in Gauss Seidel method, the updated value of x1 will be used into the computation of x2. And then the updated value of x2 will be used in the computation of x3. While in the Jacobi method, I just, when I'm performing a certain iteration, I don't use updated values. So here in computation of x2, I use x1 old and I use x3 old. And in the computation of x3, also I use x1 old and x2 old. I don't use updated values in the same iteration. Once I update all values x1, x2, and x3, I use them in the second iteration. So this is the only difference between the two schemes. Same equations, but just in Jacobi, I always use old values in computation of new values. Okay. Let me check if you have any question.
Doctor, يعني if I'm doing iteration number 2, I can take the values of iteration number 1.
Yeah.
بس when I get x1 ما بحطها بالx2.
Yes, exactly. يعني بتستعملي على طول الاولد فاليوز، هول الابديتد اللي جبتيهم ما بتستعمليهم الا لتاني iteration. Okay. سعيد, in general, if epsilon is decreasing, يعني you will converge in general. Okay. بس تبلش تشوف oscillations, يعني you might have two possibilities. أو it will diverge, أو it will have a slow convergence. Okay. Concerning Said, if it's best to use this one or the other, you should know if your system, you should try to get error. عادة إذا بلشت بالGauss Seidel method ولقيت إنه error is decreasing, you can continue with it. إذا حسيت إنه بلشت تطلع, you can say maybe it's safer to go to Jacobi method, okay, or to do relaxation as you will see after. Okay. Okay. Now, another example, use Jacobi iteration to solve for x. No, Karen, يعني ما في على طول Jacobi is better or always Gauss Seidel is better. I told you it depends on the behavior of convergence. يعني إذا أنا عندي system وعمل يعني يعني وقت بلشت بالsolution بالGauss Seidel كانت عم تعمل convergence, So على الأرجح الجاس will accelerate the convergence لأنه it will take updated values يعني حتساعد إنه نسرع. بس لما يكون عندي system already critical in convergence يعني هو it is prone to diverge عنده استعداد يكون في divergence, then الجاكوبي is better لأنه بتصير it's updating solution in a with a slower process. اوكي هلا انتم ما حتعرفوا يعني at this stage you don't know which one is better, but you should know that in general يلي بيكون السيستم يلي هو عنده اذا كان guaranteed to converge. هلا we will go over systems that are guaranteed to converge. اذا كان السيستم guaranteed to converge, then using the Gauss Seidel can be better لانه بيسرع السوليوشن. Okay, because since you are taking بكل iteration you are taking updated values and you are getting closer to the solution in a faster way. بينما as a system is not guaranteed to converge, it's more safe to go for Jacobi method. Because in general, you know, شو سبب الدايفرجنس؟ In general, the cause of divergence, and when you update, إذا في large variation بين ال updated value وال previous value, هيدا ال jump in value might cause divergence. فنحن when we don't update يعني انتوا بس تعملوا Gauss Seidel عم بتسرعوا ال update لأنه عم بتحطوا ال updated value بقلب ال calculation of new values. So عم بتبعدوا الديفرنس بين the previous iteration و next iteration, which might lead to divergence in some cases. While if the system convergence is good, then ما عنده مشكلة بيصير يقرب in a faster way to the solution. So now if we take the same example, okay, and we want to solve using Jacobi method, we will see that كمان it's not bad, it will work well, بس ال errors حيكونوا أقل بال Gauss Seidel because the system was converging in a good way. So here, for example, we'll start by the same initial guess, and we will stop iterating also for value lower than 10%. So same procedure, but the only difference now is that once we calculate x1, x2, x3 at j, we just use the values at previous iteration. We don't use the updated values. That's the only difference. So for example here, the initial guess is 0, 0, 0. So when you want to compute x1, you will use 0, 0. And also, you will not take this updated value here. No, you will take the initial guess, so 0, 0, and also for x3, 0, 0. So you don't take the updated value. This is the difference, okay? So now, so I don't do this. I just replace by guess in the previous iteration. So here I replace by zeros. I get my updated values. Now, the second iteration will use for x1 2.6167, for x2 minus 2.7571, and for x3 7.14 without using any updated value. For the initial guess, since it was 0, all approximate errors were 100%. And now we will start to see the decrease of error with iterations. So now when I perform the second iteration, as I told you, I will use for x2 this value I got from iteration j equal 1, and this is the value for x3 at iteration j equal 1. Now for x2, I don't look what I have here. I just use the value I got in iteration 1. The same for x3, okay? And finally, the same for x, to get x3, I use the old value of x2 at j equal 1. So I don't replace by the update, no, okay? And then now I am ready to calculate the errors again. So also here, I can stop directly here because the error is still larger than 10%. So I need to do more iterations. Now in the third iteration, so as you can see, both methods converge in 3 iterations. But if you just compare the values of relative error, here also they are relatively small, but still in Gauss Seidel, the error was a little bit lower. Okay. Any question on this?
دكتور
Yes.
ان جاكوبي ما فينا نقول نحن انه تتاثر اكثر بالانيشال جاز لانه هي
لا
اذا بتستعمل اكثر ولا ما انه مثلا اذا
يعني
we have an initial gas that is not
yes
انه
هلا
so
يمكن
good.
بتتأثر yes it's right إنه بتتأثر أكثر شوي يعني بالinitial gas بس at the end يعني يعني if you start with the same initial gas for both مفروض ترجع تقرب على solution for both cases. Okay يعني for the same
okay.
initial gas you should for both be close لأنه initial gas بيأثر أول 2-3 iterations بعدين بيخف الإفكت تبعه as you proceed.
اوكي يعني ما خص مثلا if we have مثلا initial gas ما منيح انه safe اكثر to use
بلا
gas.
أكيد بس أنا عم بحكي لا أوكي هلا هو الانيشال جاس إذا كثير بعيد مش منيح for the two for both methods. اوكي
yes.
بس اكيد بيأثر على الجاكوبي اكثر because انه بدنا وقت تنتخلص من الغاز يعني it takes some iterations to
yes exactly.
yes exactly.
thank you doctor.
well.
دكتور إذا سوري كنت عم تقولي بعد initial gas هو مش منيح للجاكوبين أكثر؟
ايه لأنه يعني هي شو الفكرة إنه since you
لأنه
are
ما عم بعد كثير
ايه لأنه بالinitial يعني بالأول iteration عم بستعمل completely الانيشال gas بينما بالجاس سايدل when I get new value of x1 دغري I update it when I get new value of x2 دغري I update it بما إنه بالجاكوبي I don't update يعني الجاكوبي حتتأثر أكثر بالinitial gas من الجاس سايدل ميثود but at the end يعني كل ما تعمل iteration more حترجع يخف الإفكت of the initial gas. Okay هلا for both methods if I take a very far initial gas for both methods بيصير بدي iteration أكثر يعني إذا ببلش initial gas كثير بعيد عن exact solution this will affect this is why we say we can هلا أنا in this course you are not responsible of it لأنه أنتم مش عارفين الإيكويشن شو الباكجراوند تبعهم بس in case you do you have an engineering problem you know الorder you know the order of magnitude للsolution ففيكم تبلشوا ب educated guess يعني since you nearly know مثلا الinterval or range where you might have solutions this will help you when you understand the whole equations are due to what you are putting these equations for which engineering problems you can compute you can do a good initial guess this is why we call it educated guess. But here, since we are just taking the equations, you don't know the background, the problem, I will just give you the initial guess and you will proceed with it. Okay. Any other question? Oh. Now, as I told you when we started the chapter, that we have a choice as to which equation we use for each variable. So when we took the example, I said you don't have always to take equation 1 to get x1, equation 2 to get x2, and equation 3 to get x3. You might play with equations and how to play them in a good way, because not all options are equivalent. The reason that not all options are equivalent is that we have possibilities of numerical errors. But if we don't have numerical errors, of course, it will not matter which equation to use. Okay, so just that round of errors can accumulate and can lead to variation in results. This is why we might try to use the appropriate equation for the appropriate variable. What is the criterion? In general, we have the following rule. If the equations we use correspond to a diagonally dominant matrix, then convergence is guaranteed. So we will see together what is a diagonally dominant matrix, okay? And if we can ensure that the matrix of coefficients is a diagonally dominant matrix, then we can be sure that the convergence is guaranteed. But please don't confuse it with, if you can ensure a diagonally dominant, then you are sure that you have convergence. But this doesn't mean that if the matrix is not diagonally dominant, that the solution will diverge. No. So this condition is sufficient, but not necessary for convergence. But it's good that once, if you can ensure it, then you can be on the safe side. You are sure that it will converge. If it's not possible to make it a diagonally dominant matrix, then it might converge, it might not. Okay? Now, what is a diagonally dominant matrix? The definition is as follows. For a diagonally dominant matrix, any element on the diagonal, the absolute value of the element of the diagonal, AII, is higher than the summation of the absolute values of all elements in the same row. Okay, so as you can see here, summation from J going from 1 to n. So I am changing column, therefore I'm summing elements of the same row. For J different than I, and of course I will not take the diagonal element with them because I want to have that this element will be higher than the summation of the absolute values of all elements in the same row. If it is the case, then I say it's a diagonally dominant matrix. Let us do an example. This is my diagonal here. The first element of my diagonal is 8. It should be larger than the summation of the absolute value of the elements in the same row. So it should be larger than 1 plus 2 plus 3, which is 6. Then here it's the case. So for 8, it's verified. Now for the second row, the diagonal element is minus 10. So in absolute value, I should compare 10 with, it should be larger than 1 plus 2 plus 5, which is 8. So it's true. Also, it's fine for the second row. Now for the third row, the diagonal element is 12. So I should make sure that 12 is larger than 1 plus 6 plus 3, which is the case. So also I verified it for the third row. And finally, for the fourth row, I have the element is an absolute value is 9. 9 is larger than 3 plus 2 plus 3, larger than 8. So I can say that this matrix is a diagonally dominant matrix. And then I can be sure that if I use Gauss-Seidel or Jacobi method, using this matrix, I will get a converged solution. On the other hand, if I give you the following example here, let us check if it's a diagonally dominant matrix. For the first row, the condition is satisfied. 8 is larger than 6. For the second row, it's not satisfied because 6 is smaller than 1 plus 2 plus 5. So if one of the condition, if for one row the condition is not satisfied, then it's not a diagonally dominant matrix. So in this case, I can try to do switch of rows to make it diagonally dominant if possible. If not, so if it's not possible, whatever switching I do, it will not become a diagonally dominant matrix. It's fine. I will take it as it is, and I might have convergence. Okay. Now, how we can try to make it a diagonally dominant matrix? Let us take an example. So if we take the following example, if we take the matrix as it is, it's not diagonally dominant because already from the first row, if you take the diagonal element, already it's smaller than 13. So of course it will be smaller than the summation. Then it's not a diagonally dominant matrix. But I can try to switch rows to convert it into a diagonally dominant matrix. And when I do switching, this means that I will use an equation different than equation 1 to get x1. So this is why I told you don't have always to use the first equation to get x1, the second to get x2. Because when I do pivoting now, I will pivot, let's say, the first and fourth equation. So now the fourth equation will be used to get x1. Why I'm doing this? Because I look, for example, for this row, I can see that 23 is a large element. So I will try to put it as a diagonal element. To put it as a diagonal element, it should be in the first, this equation should be in the first place. So if I switch now 1 and 4, then I will have the big element 23 here and 13, which is also high here. Now I will check that 23 is larger than 2 plus 3 plus 9, and 13 is larger than 2 plus 1 plus 8. So until now for these rows, it's fine. Now let me check the second and third row. For the second and third row, it's not working because here I have 6, which is smaller than 1 plus 15 plus 5. So it's not working. So I should try to switch. I can now try to switch 2 and 3. It will work now because in this way, switching allowed me to have a high element on the diagonal here. So 11 is larger than 1 plus 2 plus 3. And 15 is larger than 1 plus 6 plus 5. So I was able, by doing some pivoting of the rows, I was able to create a diagonally dominant matrix. So now it's safer to work with this system. Okay, so it's not always possible to reach it, but in case it's possible, it will guarantee convergence. So this is the first strategy to guarantee convergence. Now, another strategy, but that will not always work, is relaxation, and we will talk about it now. So in general, relaxation is used to help ensure and or accelerate convergence. So it can be used in two scenarios, or if I have divergence, I will try to do under relaxation, and we'll define now what is under relaxation and what is over relaxation. So I do under relaxation to help into having convergence if my system is prone to diverge. And in case my system represents a very good behavior in convergence, I can try to accelerate convergence by doing over relaxation. But keep in mind that this technique is not always successful, not as the previous method. The previous method, if I ensure a diagonally dominant matrix, I can guarantee convergence. This method of relaxation can work sometimes, but in some cases it will not. So I can try it to, if I have a divergent system, I can try it to have convergence if possible. So in this case, this technique consists on modifying each variable after each iteration, and we will see how we modify. Okay, what is the idea? The idea is that whenever we calculate a new value, okay, we can take it as it is, or we can put it as a combination of the new value and the old value. What is the idea here? So for example, as I told you, in case you have a system that is prone to divergence, this can be due to the fact that x, when updated, delta x is very large. So it's updating in a fast way that it is causing divergence. In order to not take the full variation of x, I can say I want to take a proportion of x new and a certain proportion of x old. So instead of taking 100% of new value, let's say I will take 70% of the new value plus 30% of the old. So when lambda is between 0 and 1, this is under relaxation. Under relaxation means that I don't take the updated value as it is. I reduce its effect by taking a percentage smaller than 100% for it, and I divide the percentage between the new and old value. Okay. Now, if I take lambda just equal to 1, this means that I'm not performing any under relaxation, no change, no relaxation, because I'm taking the updated